Welcome. In this video I'll give an outline of the derivation of CGL MHD, and in the last video I went through a kind of heuristic arguments why the CGL closure is useful in terms of the conservation of the first and second adiabatic moments. In this video I'll show in a little more detail how the equations can be derived from the Vlasov equation and what assumptions you're making when you use the CGL approximation. And the main one is that the heat fluxes are neglected. So like MHD, it's assuming zero heat flux. Now in general, of course, this is not correct, and this is not rigorously derived in any way, but these equations still remain useful for calculating kinetic corrections to MHD, particularly kinetic corrections involving anisotropic pressures. Now the main resources I've used for this, there's a recent paper on archive which reviews CGL MHD, and that's extremely useful. There's also a section of Friedberg as well which deals with CGL. So it's essentially a collisionless theory for collisionless plasmas, and so we're going to start with the collisionless Vlasov equation, where here this equation is the same as before in earlier lectures. F is a distribution function which depends on time, 3 dimensions of space in general, and 3 dimensions of velocity. Now here is the kinetic velocity v is a coordinate, and so this gradient v is the gradient in velocity space. So this might be written also something like d by d dv. So what's meant is gradient in each of the velocity dimensions. And note here there's no collisions, so here we would have a collision term if you had a more general equation. And as before, we now take moments. So we can take moments of the 0th moment, for example, gives us density. So if n is just the integral of the distribution function integrated over all velocity, and that gives us some function of time and space because we've integrated over all the velocities. And then of course we use that if you want to know the density times the velocity, we take the first moment, so this is v times f dv. So take the first moment, and then the second moment gives the pressure, and so we have the pressure tensor in general. Now here you have a component of mass because we need a force essentially. We need some kind of momentum, so we have a mass. And now here we end up with equations which depend on the difference between the fluid, the kinetic velocity, which is v of the velocity of the particle, and the average speed of the fluid, or velocity of the fluid, which is this u here. So this is the fluid. So this is the fluid, whereas this v here is the coordinate. So essentially the kinetic. So it's the difference between the velocity of a particular particle and the average velocity of the fluid. And then we have essentially several of these, again multiplied by f and integrated up over all velocity space. Now here we have two velocities, or two vectors next to each other. So here we have something like a vector and another vector. In this case they're the same, but in general we have two vectors next to each other. We're going to read this as a tensor. So this is like a, I, b, j. So it's a two-dimensional tensor, so a matrix with one index is the first vector and the second is the second vector. And this gives us a rank 2 tensor. i.e. a matrix, and this can be continued to higher orders. So in general we have also a third order tensor, which is kind of the heat flux. This is kind of the pressure tensor transport, so it's how the pressure tensor moves around in space, and write this as basically a 3 tensor like this. Now we have 3 vectors next to each other, so this is a rank 3 tensor. And again integrating over all velocity space. So we have a rank 3 tensor, so we're going to try and remember to underline it 3 times to say it's rank 3. And P here I've underlined twice, so it's a rank 2 tensor. I'll just try and be consistent with notation. So we have these moments, distribution functions. What we want to do now is apply these same operators to the Vlasov equation. So to calculate the pressure equation, for example, we multiply through by this v minus u twice, and then integrate over all velocity. And it's helpful to define this velocity called w in earlier lectures, which is this v minus u. So it's the speed of a particle relative to the fluid motion. So if you do this, so you apply multiply through by w twice, and then integrate over all velocity. A lot of manipulation and mathematics later, you end up with an equation for the pressure tensor. Okay, so the notation here needs some explaining because it's a bit unusual. Well, it's usual in this field, but may not have come across it before. So firstly, this S superscript. So this whole thing is well, in fact, every term in this equation is a rank 2 tensor. So it's a matrix equation. And the notation here is that some quantity A, which is a rank 2 tensor, so a matrix, to the S is just A plus A transpose. So you can basically take this equation and add another 2 terms here with the transpose. It's the same as this. That's what this S means, just to save it as space. Then, for example, when we have this, so divergence of U times P. So here we're applying a gradient or divergence operator on a rank 3 tensor. Taking the derivative of this, what's in the brackets here, but the contraction is with the first index here. So this, if you write it in index notation, it would be something like dk. So it's adding up over the k index, where k corresponds to the velocity here, and pij. Similarly, when we have divergence of q, so divergence of q, now q is a rank 3 tensor, which again depends on, this is, again, q is now rank 3 and it's contracting over the first index. This p dot grad u, so here p is a rank 2 tensor, u is a vector, and what this is doing is the dot product here is with the second index of p. So this you can write as p I k, and then the derivative index k. So that's this operator here is made a differential operator, and the u is the uj. So this makes a rank 2 overall. This makes a rank 2 tensor by contracting over the k's here, so summing over k. And then finally this b crossed, so taking a cross product of a vector and a matrix, so rank 2 tensor. This is again is just with the first index of p. So b cross p is a tensor. So this you can write as this. So we have the first index is going to be the first index is going to be this, and then we have 2 indices which are going to be summed over, and this is going to be corresponding to the b, so bk, and pl, so that's this index here. So these 2 indices are being summed over, and pj. So it's the first index of p here which is operated on, and the second index survives, and the overall result is just depends on ij, as to all of these other terms too. So hopefully this notation is reasonably clear. If it helps to translate it into index or indices, this is how you do it. Otherwise, essentially, the convention here is that operators are on the first index of tensors. Okay, so this so far has made essentially no assumptions. So we've just taken the collisionless Vlasov equation So that's the only assumption really so far, that there are no collisions. And we've then just taken moments of it, so we've taken the second moment to calculate the pressure tensor, and the third moment to calculate the heat flux, or the pressure tensor, transport tensor. And now we can start to make some approximations. So the first thing is to look at the terms in this equation, and in particular we can look at this term here. So we have the magnetic field cross the pressure tensor, and we're going to compare that to this term here, which is the rate of change of the pressure tensor. So particularly this is basically charge times magnetic field over mass. This is the cyclotron frequency, and so we write down that Q over M times B cross P. So that is basically, the magnitude is the cyclotron frequency times the pressure. This is kind of magnitude. And if you compare this to this term here, so d by dt is like a frequency, like a wave frequency. So d by dt, this is like a wave frequency times the pressure tensor. And so if we're in MHD regime, or if we're in any kind of regime where the wave frequencies are much less than the cyclotron frequency, so if you want the wave frequencies to be much less than the cyclotron frequencies, because we're averaging out over the cyclotron frequencies, then that would imply that this term, the derivative in time, was much less than this term here. And in fact, this term would be bigger than everything else. So this term here would dominate over everything else if the cyclotron frequency becomes high. So because this is the only bit that depends on say charge and mass. So if cyclotron frequency is high, this term dominates, and so the argument is that there must be another reason why this goes to zero, or why this becomes very small. Because if it doesn't go to zero, then it becomes bigger than everything else, because this factor in front will be huge. And so this term must either go to zero, or it will completely dominate the solution. So there must be another reason why there's some reason, something to do with the solutions, which means that this is a small quantity. And the reason is actually that the pressure has some structure to it, so it has some, it's in fact gyrotropic, is the reason we're going to come to very shortly. But one way of making this zero, so if you want this term to be zero, one way is in MHD. So if you make that the pressure tensor is just a scalar times a density matrix, then this is just isotropic. In that case, this term, and I have to remember that this is also combined with its transpose, because it's under this S operator, so we have this term plus its transpose. So we have, so the terms that actually have to cancel are Q over M, so P cross P plus its transpose, and this then goes to zero if the pressure is isotropic. More generally, another way of making this term go to zero is if the pressure is gyrotropic. So if it's constant around the gyro orbit. So when particles are moving around on their orbits, it doesn't matter where on the orbit they are, the pressure is constant. So this is B here. We have a particle on an orbit. And it has some kind of gyro phase, so some kind of angle here theta. This is gyro angle theta. So depending on where it is, where the particle is on this angle, the pressure is constant, and then it's gyrotropic. And to get this, we have to have the pressure is again some kind of a parallel pressure, plus a perpendicular pressure, which is the identity minus BB. And this is the closure that CGL uses. So CGL MHD uses this. there may also be a small correction. So the stress tensor. So if there is some variation, this can lead to a stress tensor. But in general, this is the way of making that term, making this term here go to 0. If you have just a pressure which is constant around the gyro angle, and then you can obviously have small corrections. So therefore, if we know what P is, or have an equation for P, we can calculate P parallel by taking the dot product of P with B. So we just take the P parallel is the pressure tensor. I'm going to call this double dot BB. So BB here is a rank 2 tensor. So this here is, say, Pij, so it's 2 indices. This is also a rank 2 tensor. This is Bij, so it's 2 vectors next to each other, so we're going to call this a rank 2 tensor with 2 indices. Double dot just means essentially the dot product with the first index of this and the first index of that one, and the second index and the second index. So this double dot just means contracts both the first and second index like this. And so here we have P parallel. These B's are unit vectors, so this dotted with B, for example, is 1 if it's along the field, and that cancels out all this stuff too. In the same way, we can calculate the perpendicular pressure by taking the double dot product between the pressure tensor, and now we just want this component here. So the identity matrix minus B times B. And here we need a factor of 2. You can see this most easily if I just write out what P looks like. So P, so I have 3, it's a 3 by 3 matrix. One of them is the parallel direction, so I see P parallel, and one of them is P perpendicular. And so when you do this contraction, you sum over all the indices. If it's the parallel component, there's only 1, and so we have a 1 factor here. If you're summing over all the perpendicular components, there are 2 of them here, and so you get a factor of 2 that you need to divide through, as that gives you the perpendicular component. This also gives 2 constraints on what this stress tensor must look like, because obviously when we take the dot product with BB, this must go to 0, and the same when we take the dot product with this. So this must have, so the stress tensor double dot with BB must be equal to 0, and also the stress tensor with I minus BB must be equal to 0. And because it's just linear operator, you can actually use this and just rewrite this as saying that this double dotted with the identity matrix is 0. Actually, if you think about what this is, if this is the identity matrix, that's just the Kronecker delta, and so what this is doing is actually just taking the trace. So this is just the trace. So the sum over the diagonal of the stress tensor equals 0. Okay, the stress tensor has 0 trace and has this component, so there's nothing in the parallel direction. Okay, so that's the more general form of the pressure tensor. So if the pressure tensor has this form, then we can make this component here small, and so it no longer dominates the equation. So the next part of the calculation is to essentially apply these operators. So we want to work out from the pressure tensor what equations for the parallel pressure are, and from the same pressure tensor equation we want to work out what the perpendicular pressures are. So we take the equation we've got here for find it here. So we're going to take this equation here, which is the equation for the pressure tensor, and we're going to take the double dot product with BB to work out the parallel pressure, and the double dot with the identity minus BB to work out the perpendicular pressure. And after a long calculation, you end up with these equations. And for the perpendicular pressure, you get... So we end up with these quite large equations for the parallel and perpendicular pressures. And so far we've just assumed that there are first no collisions, so we drop that at the beginning. Then we've taken the limit of high cyclotron frequencies, and in that limit the pressure has to become nearly isotropic or gyrotropic, so pressure constant around the gyro orbits. Using that, we've been able to show that the pressure tensor should look like a combination of a perpendicular and parallel pressures, and then these are the equations that describe them. So this is valid in the limit of low frequency compared to the cyclotron frequency, and valid in the low collision regime. But you see that they're quite complicated expressions, and they depend on these pressure tensor transport coefficients Q and these stress tensor components pi, and now what the CGL limit is essentially to set all these to 0. So CGL we say Q is 0, so CGL sets Q equals 0, and also the FLR components, so stress tensor 0. So all these terms here go 0, and we're just left with this first part here. Is the CGL equation for the perpendicular pressure, and the same for the parallel pressure. So these terms here with the stress tensor and the heat flux, these are neglected. So these terms here are gone, and then the component which is kept is just these parts here. So the CGL equations are simplified from the full set of equations, and they're using this kind of adiabatic assumption that there's no heat flux. You then end up with two equations for parallel and perpendicular pressures, which are relatively simple, and these are probably the simplest equations that you can have which have these separate parallel and perpendicular pressures. So it's a simple extension to MHD. But if you want to really capture more detailed kinetic physics, you need to include some of these other effects here.